So since we saw in skill 4 that we can evaluate a logarithm and it is the inverse of an exponential function, that's going to help us with graphing. Okay, so take a look at A. It is the function y equals 2 to the x. So if we were to substitute in -3 for x, we would get 1/8. -2, 1/4, -1, 1/2. Again, those are all fractions because of that negative exponent property. Anything to the 0 power is 1. 2 to the first is 2. 2 squared is 4, and 2 to the third is 8. The equation of the asymptote, and if you want to write down that it is a horizontal asymptote as a reminder, is at y equals 0 because we were given a parent function of base 2 without any transformations. Therefore, we have y equals 2 to the x, which is table. Now, if the log function is the inverse, based on the relationship between inverses, where we know their domain and range elements switch, they reflect across the line y equals x when they're graphed on the same plane. If we think about that, well, the log base 2, base 2, is the inverse of that exponential function. So we can switch the x and y's because their domain and their range elements switch by definition of an inverse pair. So our x's now are 1/8, 1/4, 1/2, 1, 2, 4, and 8. And the y values are -3, -2, -1, 0, 1, 2, and 3. Which makes sense because let's take this last column for example. If I asked you to evaluate the log base 2 of 8, just like we did in our skill 4 notes, you're looking for the exponent that would make 2 to that exponent equal 8, right? We're always looking to evaluate to the exponent. So the base, which is 2 to what power is 8, boom, it's 3. So that's why this is our input and our output. Now, if an exponential function has a horizontal asymptote, it follows suit that, it follows suit that a logarithmic function will have a vertical asymptote, and it will be at x equals 0. Now, for the exponential functions, we always had a horizontal at y equals k. For our logarithmic functions, we have a vertical at x equals h. Let's graph it, ladies and gents. Let's do it. Okay, so it says to graph both the log and the exponential on the same plane. That's so we can see how they relate to each other. So I'm going to go ahead and graph y equals 2 to the x in blue. I know that I have a horizontal asymptote because it is the parent function of an exponential function. We have points at -3, 1/8, -2, 1/4, -1/2, 0, 1, 1, 2, 2, 4, 5, 6, 7, and 3, 8. We get crazy close to that horizontal asymptote. We do not cross it. The graph is representing exponential growth with arrows at the end. Okay, so for the logarithmic function, I'm going to do that one in purple. It has a vertical asymptote. Okay, so I'm going to draw my vertical asymptote. These must be drawn on all of your graphs because they are characteristics of those graphs. If they're on the axes, as they are here, then you can either extend out like I did, use a different color so it's easily visible, or do it a little bit above or below or to the right or the left, depending on where that asymptote is located. Okay. All right, plot these points with me, please. 1/8, -3, 1/4, -2, 1/2, -1, 1, 0, 2, 1. Oh, that's not 2. Yep, I can count. There we go. 4, 2, and 8, 3. Starting from the bottom, curving up, making sure we don't cross that vertical asymptote. Vertical asymptotes, by definition, cannot be crossed because they represent where the function's undefined. And for the same reason, we can't cross the horizontal asymptote for the exponential function. That applies here as well. Okay, if you would like to see the reflection of the inverses across y equals x, you can always sketch that in so that you can see that they truly are, if my graph had a straight line, reflected across that line. Nice. All right, so there's a little introduction to it. Let's get right into graphing these two examples. Enter in our Cartesian catalog. All right, so as we saw on the note guide for base 2, that's what we're going to be using as our guide. Okay, let's go ahead and create the transformation table as what? Create the x and y table as if we haven't seen this before. Now, with exponential functions, we have to most certainly identify the base. For us, this is going to be log base 2. So, what am I going to do? Well, I'm going to create my x and y table. Remembering that since this is the inverse of an exponential function, my y values will now go from -2 to +2. For the exponential functions, the x's went from -2 to 2. Now, for their inverse functions, the logarithmic functions, their y values are going to go from -2 to +2. Okay, and how do we calculate? Well, my base is 2. So 2 to the -2 power is 1/4. We are working backwards. 2 to the -1st power is 1/2. 2 to the 0 is 1. 2 to the 1st is 2, and 2 squared is 4. Keep in mind, these have vertical asymptotes. I'm just going to write it next to the parent table. And this one is at x equals 0 since my h is 0. I know, we already graphed this, but let's graph it again so that it's on our Cartesian catalog. Okay, so then we have 1/4, -2, 1/2, -1, 1, 0, 2, 1, and 3, 4, 5, 6. There we go. It is going to start from the bottom up. We're not crossing that vertical asymptote. I understand that it gets really close. We don't want to cross it. And then we have all of our characteristics to fill in. So identifying hk, it is not a point on our function. So we can, yes, write it in coordinate form, or we can write h is equal to 0, k is equal to 0. There isn't an x-intercept because the vertical asymptote, oh, what? Totally wrong function, Patterson. There is an x-intercept, unlike the exponential function. See how easy it is to get the two confused? Whew, really take your time. And it's in our table of values, so we'll write 1, 0. For this one, think about your exponential functions. There wasn't an x-intercept because there was a horizontal asymptote on the x-axis. Now, inverse functions, domain and range values switch. So now there isn't a y-intercept because the asymptote is on the y-axis. Okay, now domain and range, well, they're going to switch from the exponential. So the domain of a logarithmic function will be similar to that of the range for an exponential function, which makes sense. This starts at the asymptote and goes to infinity. Non-inclusive because it doesn't include 0. The range, however, goes from -infinity to +infinity. Okay, increasing and decreasing intervals. Remember, this is always stated with your domain elements. As x goes from this interval to that interval, where do our y values go? Well, as x goes from 0 to infinity, our y values are increasing, which makes sense because its inverse is exponential growth. So a base of 2 being greater than 1 is going to have increasing intervals as long as there aren't any reflections. Okay, is this 1-to-1? Yes, it most certainly is. The rate of change varies because it's not a constant, consistent rate of change. There is not an axis of symmetry. We don't have a minimum or a maximum value because the graph is not restricted in those regions. There isn't a horizontal asymptote, but we have a vertical asymptote at x equals 0. Woohoo! All right. So let's look at logarithms with transformations. Similar to the exponential function, we need to be careful. There are two different b's. Capital B is the base. Little b is the transformation. So please do not list the base as a transformation. It is not, okay? It just tells us, are we growing or decaying, and what the parent function points are. All right, so looking at this particular example, the second one on our Cartesian catalog, there isn't a b value we need to factor out. So I'm going to go ahead and state a as 2, meaning that we have a vertical stretch. I'm going to list b as, ooh, should we list it? You can. But no, b is 1, so we don't need to. H is -3, which means we go 3 units left. And k is +1, meaning that we go 1 unit up. Using the transformation table that we've been using all year, yes, ladies and gentlemen, the blueprint doesn't change. So we're going to have x minus 3, reciprocal of b, plus or minus k or h, and then a, so 2y plus 1. A times y plus or minus k. As always, I'm going to go ahead and put the parent points next to my transformation table. It's a little bit easier for me, and we've talked about this, just to have it right there to see it. You guys do have it on your page. Okay, so if we take 1/4 and substitute it in for x, we get 1/4 minus 3, which is -2 3/4. 1/2 minus 3 is -2 1/2. 1 minus 3 is -2. 2 minus 3 is -1. And 4 minus 3 is 1. For the y values, if we take -2 and substitute it in for y, we get -4 plus 1 is -3. If we substitute in -1, we get -2 plus 1 is -1. 0 gives us 1. 1 will give us 3, and 2 will give us 5. The last thing I like to do is note where that vertical asymptote is going to be. It's at x equals h, so x equals -3. Nice. Let's graph it, ladies and gents. Go 1, 2, 3 to the left and draw in that vertical asymptote. The points start at -2 3/4, -3. 1, 2, 3. So do the best that you can to get as close as possible to that accurate point. And keep going. Starting at the bottom, because there wasn't any reflection, and going up, there is our second graph. Still base 2, but it's nice to see it with some of the transformations. Okay, listing out our h and k, well, yes, we definitely list that out at the beginning, which is nice to go back and pick it up. So h is equal to -3, k is equal to 1. Again, if you like having it in coordinate form, that's fine. Just know it's not an actual point on the graph. The x-intercept, ooh, there is one, but we need to solve for it. How do we solve? Well, we plug 0 in for y, and we isolate the x. So plug 0 in for y, please, and then we have 2 times the log base 2 of x plus 3 plus 1. Okay, isolate the logarithmic term with me, because we need to get x by itself. X is inside of the log quantity. So I'm going to subtract 1, and that equals 2 times the log base 2 of x plus 3. And then I'm going to divide both sides by 2. So we get the log base 2 of x plus 3 is equal to a -1/2. Well, shoot. I have a logarithm of my variable equal to a number. Remember skill 4? When we were introduced to logarithms? That's right, ladies and gentlemen. We can rewrite this exponentially. What? The base is 2. The exponent is a -1/2, and it equals x plus 3. Oh, beauty of mathematics. Now, a couple things. First off, that negative exponent needs to go away. So x plus 3 is equal to 1. over 2 to the 1/2 power. And then 2 to the 1/2 power, flashback to first semester, is a rational exponent. So it's truly 1 over the square root of 2. The denominator is the index. The numerator is the exponent. And then we need to rationalize because that's how we roll. And we can't have a radical in the denominator. So we get x plus 3 is equal to the square root of 2 over 4. Did you catch it? Good. Yep. When we multiply radicals together, ladies and gentlemen, they cancel each other out and you are left with what is underneath. Hopefully you have rad 2 over 2 on your paper. And then last but not least, subtract 3 plus the square root of 2 over 2. Now, if you're wondering why we don't have a plus and minus, it's because we did not choose to take the square root. I'm not solving for a variable that looks like this. X squared equals 9. What is x? Well, if I take the square root, it could be plus and minus 3. However, down here with our x-intercept, it's 2 to the negative 1/2 power. It's a number that's already being square rooted. We're not choosing to apply that. Okay, so that's why we don't use the plus and the minus. We need to make sure that we write this as a coordinate. So negative 3 plus the square root of 2 over 2 comma 0. Please do not approximate. We want it in exact form. Okay, y-intercept. It looks like there's one, but it's not in my table. So mathematically, we get to find it again. Oh, the joys. So y is equal to 2 times the log base 2 of, plug in 0 for x, since this is the y-intercept. And if we keep simplifying, we get 2 times the log base 2 of 3 plus 1. Ladies and gentlemen, can we raise 2 to some power and get 3? Can I evaluate that logarithmic term? Well, 2 to the first is 2. 2 squared is 4. Nope. So our x-intercept is going to be written as 0, comma, 2 log base 2 of 3 plus 1. All right. Well, the domain definitely is going to start at that vertical asymptote. Again, we are not including it, so it's a parenthesis negative 3 to infinity. The range is negative infinity to positive infinity, all real numbers. It has a base greater than 1. So yeah, it's increasing, and we don't have reflection, so it is increasing. Negative 3 to infinity. It is not decreasing. Yes, it is 1 to 1. The rate of change varies. We do not have an axis of symmetry. We do not have maximum and minimum values because it's going up to positive infinity and down to negative infinity. We do not have a horizontal asymptote because this is not an exponential function. It is the inverse of 1. So our vertical asymptote is at x equals negative 3. Nice. Okay, so we've done 2 examples, one being the parent function with a base of 2. Now, before we get to the third example, just a reminder that we do have to find the parent function table points before we graph every time, just like with the exponential. Okay, it just so happens that for this Cartesian catalog, it's a base of 2 every time. Okay, so you might want to write that down, make a note to yourself, find the parent function points first. All right, last but not least, we need to factor out the b value. So negative 3 times the log base 2 of 2 times x minus 2 minus 1. Nice, there's a lot going on here. Okay, so I'm going to go over to the left-hand side, and I'm going to practice identifying the parent function. It needs to have the same base, but no transformation, so log base 2 of x. This is the inverse of an exponential function, so my y values go from negative 2 to 2. Since my base is 2, 2 to the negative 2 power is 1/4. 2 to the negative first power is 1/2. 2 to the 0 is 1. 2 to the first is 2. And 2 squared is 4. Let's identify the transformations, you guys. All right, given we have a is negative 3, so it's negative 1 times 3. There are 2 transformations here. The negative is a vertical reflection. This is great, so you guys have the chance to see how a reflection affects a logarithm. And we have a vertical stretch because a is greater than 1. The b that's in the equation is 2. We'll put 1/2 into the table of values. So that means we are going 2 units to the, oh, hello, I was looking at h. That means that we have a horizontal compression. All because the reciprocal of 2 is 1/2. Now, h is 2, here we go, which means we go 2 units to the right. And k is -1, meaning we go 1 unit down. Setting up that transformation table, here we go. So we have the reciprocal of b, 1/2 times x plus h, which is 2. And then we have -3 times y minus 1. Taking our parent function table points, okay, 1/4 substituted in for x, we get 1/8 plus 2, so that's 2 1/8. 1/2 is 1/4 plus 2, so 2 1/4. 1 gives us 2 1/2, and go ahead and finish the table on your own as I'm finishing it here. Go ahead and actually pause the video, please, and then press play when you're ready to go. Hopefully you were able to fill in the table okay, and you have now pressed play. Something else I'm going to state is that the vertical asymptote is at x equals h, so x equals 2. You know I always like to have that written. So go ahead and graph that with me, please. X equals 2. And then plotting the first point is 2 1/8, 5. So 2 1/8, 1, 2, 3, 4. This is the starting point, and this is going to connect to the rest of the points in the curve. Okay, if you need to, you can always star it as a reminder. And then 2 1/4, 1, 2. Keep graphing with me, please. 6, 7. Hopefully my math is right. Hopefully yours is too. So remember, we start at that first point and then we go towards the additional points, connecting them in a curve and extending up, not crossing that vertical asymptote. All right, ladies and gentlemen, let's fill in the characteristics, yeah? H and K were previously identified. H is 2 and K is -1. Again, you can put it in coordinate form if that is your preference. There is an x-intercept, but we don't know what it is. So to find the x-intercept, let's plug in 0 for y. I need to scroll up so I can see the equation. All right, so 0 is equal to -3 times the log base 2 of. At this point, as we've mentioned so many times before, you can use the factored out form or you can use the given. It doesn't matter. They're representing the same function because nothing was canceled out or reduced. Okay, I'm going to add 1 to both sides. So 1 is equal to -3 times the log base 2 of 2x minus 4. Why am I adding 1? Because I'm trying to isolate the quantity that has the variable inside of it. I'm going to divide both sides by -3. So log base 2 of 2x minus 4 is equal to -1/3. Well, here we are again. We have a logarithm of our variable. We can, however, rewrite it into exponential form. The base is 2. The exponent is -1/3, and it equals 2x minus 4. Similar to the previous example, let's go ahead and apply that negative exponent property. So we get 1 over 2 to the 1/3 power. It is a rational exponent, which means 2x minus 4 equals 1 over the cube root of 2. And since our index in the denominator is 3, we need 3 2's in order to rationalize. So I'm going to multiply the top and the bottom by the cube root of 4. That leaves us with 2x minus 4 equal to the cube root of 4 over 2. Nice. Yes, you must always rationalize if you're questioning. And then I'm going to add 4 to both sides. So 2x is equal to the cube root of 4 over 2 plus 4. We then need to divide everything by 2. Keep in mind, we have a fraction on the right-hand side. So a fraction and a fraction with a fraction is a lot of fractions. So what I'm going to do, instead of dividing, is I'm going to multiply both sides by the reciprocal. This still allows me to isolate x, and I can distribute. So I end up with the cube root of 4 over 4 plus 2. And that's going to be our x-intercept. So writing that as a coordinate, we end up with the cube root of 4 over 4 plus 2, comma 0. There is a, there isn't. Be careful, okay? Just like with exponential functions, we sometimes don't have x-intercepts. Sometimes with logarithmic functions, this is a perfect example, we don't have y-intercepts because the graph is on the right-hand side of the asymptote and the asymptote is on the right-hand side of the y-axis. So we're going to put NA. Ooh, not in that color we aren't. And the domain, starting at the asymptote going to the right, there wasn't a horizontal reflection, so we're still going to the right, is at 2, comma, infinity, still a parenthesis because we're not inclusive. The range is all real numbers. Now, this was increasing, but there is a vertical reflection. So if you have a base greater than 1, your graph is increasing, unless you find that there is a vertical reflection. So now we're going to decrease from 2 to infinity. And this was similar to the exponential functions with growth or decay. Those reflections definitely had an effect on that. It is 1-to-1. The rate of change varies. And for reasons we discussed on the previous 2 graphs, we don't have an axis of symmetry. There isn't a minimum or maximum value. Since there isn't a horizontal asymptote, this is not an exponential function, ladies and gentlemen. We'll put NA. But we do have a vertical asymptote at x equals 2. Please make sure that you write it as an equation. That is so important. Sorry for the noise. My cat is trying to get into a bag. Please, please, please do not attempt the homework. Okay, maybe a problem. We will take class time to do that, answer any questions you may have, and work on it so that we really have a good grasp of it. All right, guys. See you then.